work. You can see my slides, I hope so. Then let's start. So I will give you a lecture on the possibilities of synchrotron-based X-ray absorption near-edge structure spectroscopy, also called XANES spectroscopy. And I will try to convince you that this technique is a powerful tool to assess the classification and cycling of important bioelements in soils and also in other environmental samples. In soil science, it's very important to know not only the element content of an element of interest, but also its speciation, because the environmental effects of nutrient or noxious elements in soils are often dependent on the species. It can be the element oxidation state or binding form or the combination of both. And this is the problem of many current wet chemical techniques, which have been used in former times. They often yield operational defined fractions, which are poorly defined rather than exact species. Additionally, in soil science, it's very important to know the spatial heterogeneity of a given element and the species, because average values don't count too much. So everybody knows this. So if I have one hand in boiling water and the other in ice, would be on average about maybe 50 degrees, or let's put hot water 80 degrees. So I have an average of 40, which is nice. But the situation on a given point can be quite different. So it's important to really address the element speciation and element concentration, not in an average soil, but at different points in the soil profile. And this is also a limitation of current wet chemical techniques, because the techniques need a certain amount of samples. And if you need that amount, and you can't go further in spatial resolution until you have collected this necessary amount. And this is one of the powers of XANES spectroscopy. I will show you in a minute. You can do these analysis with much less material than ordinary wet chemical analysis. There's very many strengths of XANES spectroscopy. First, it provides a direct, non-invasive element speciation without sample pretreatment except grinding. Second, in many cases, you get an unambiguous assignment of the synchrotron signal, maybe absorbance, maybe fluorescence, maybe transmission, to different species, depending on its energy of the signal peak. Like here for chromium-6, which is highly toxic, and chromium-3, which is rather harmless, you can clearly differentiate both chromium species by their peak energies of the main feature, which often is the white line, but not always. And if you conduct these analyses carefully and use appropriate protocols, you can really speciate elements with a high accuracy and precision, with errors down less than 10%, or even in some cases less than 5%. Of course, this depends on the element under study, and you have really to conduct adequate sample operation and spectrum deconvolution techniques. And finally, as pointed out before, you can really work with small sample amounts, less than 1 milligram are sufficient, which allows you to work on soil fractions, which are hard to acquire. And you can use dry or moist or liquid or even oxygen sensitive samples. I will give you an example later, but there it's complicated to prepare the samples and also in many instruments to run them. Regarding the spatial heterogeneity of element concentration and speciation, the small amount of sample which is needed allows for fine-scale sampling and analysis at a profile scale. So normally in soil science, we take profiles, which is pits, and then we analyze different layers of the soil profile. Here's the topsoil, here's the surface, and then you go deeper. And if you need small samples, you can collect very many spots in the soil profile and address the spatial heterogeneity, here in this case of different phosphorus species. I will go in detail at a later stage in my talk about this example. And you can go even finer in scale if you apply micro XRF or micro XANES, which will not be my topic today, but I did experiments on spectral microscopes and addressed the spatial resolution of phosphorus and other species on a microscale. Here's an example from a peat sample from a German peat. We have micro XRF images. Here is the scale, 10 micrometer, and you see different elements are enriched in different places of the sample. And then you can take XANES spectra at different places. We were interested in sulfur here, and you see, for example, the sulfur spectrum at microsite 1 is very different from that at example microsite 4. Here is more reduced, here more oxidized. So you can really differentiate element speciation at a submicron scale with that. And you can do even more, which I haven't done so far, but you can do it. You can also address temporal changes of element speciation at very small levels of time. If you use fast reacting monochromators, which allow a spectrum acquisition within far less than a second, you can really in situ monitor changes of element, changes of speciation of different elements within microseconds and even less. Particularly if you combine these fast time resolving spectroscopy with devices which allow, for example, contact of one soil compartment with a liquid, so that you can really look at the just going on reaction. Of course, as any other analysis, also XANES has some problems which have to be addressed when you're doing experiments in soil science. First, in soils, this is a particular problem of soils. The exact composition and element speciation of your sample, in contrast to material science, often is very poorly defined or even completely unknown. So you have problems with the selection of the appropriate standards. And if you know what standard you would like to have, you don't always get it. So you have to prepare it and yourself by chemical reactions. And you often are encountering problems with spectrum deconvolution, which are more complicated than in material science or chemistry. Also in soil samples, you often have the problem of radiation damage effects. This depends on the element under study. Particularly sensitive are elements which occur in soils in different oxidation states, like sulfur. And a particular problem of soils is that for some elements at least, low concentrations complicate or even prohibit analysis completely. This depends on the elements. Sulfur normally doesn't create problems, but phosphorus or other elements which are important but present in low concentrations may cause problems during analysis. I will give you an example later. And finally, you always have to make the choice between two evils: self-absorption if the concentration is too high, or sample permeability if you want to study the same sample in transmission. And you have to navigate your ship of analysis between these two evils to minimize confounding effects. Nevertheless, as I will show you, XANES spectroscopy on soils is very nice to have and very nice to do, and I will give you several examples in the next minutes. I will start with sulfur, which was my first XANES work, and which is a very comparably easy element because spectrum deconvolution is comparably simple. But it's redox sensitive, as I mentioned, so you have to be careful with sampling and sample pretreatment and analysis if you encounter soils where there could be reduced sulfur fractions available. Then I will give you some example about iron, which is closely related to my sulfur work. I used the same samples, and iron is also redox sensitive. And XANES allows, at least for discrimination between ferrous and ferric iron, for a more detailed analysis, you often have to use XAFs. I will show you an example later. Then I will switch to phosphorus, which is methodologically much more challenging due to its low concentrations and poor spectral features. And finally, give you a very short glance on my most recent work, which I just did a couple of months ago, which hasn't been done so far in soil science, is calcium XANES. So starting with sulfur. No, first, I will show you where did I work. I started my career at the Beamline 21 at the ESF in France. It has a range of work between 2 and 9 keV, so you can analyze phosphorus up to copper with KH XANES. And after a couple of years, I switched to Vantanas Beamline, to Beamline 8 at SLRI in Thailand, in Nakhon Ratchasima. Very nice instrument. Oh, I mixed up the pictures. Oh, I'm sorry. This is, of course, Thailand, and this is ESF. I'm sorry for that. Okay, but the instruments are correct. You can approach an even wider range of energy at BL8 from 1 to 13 keV, which allows K chains from magnesium up to zinc, which is a very broad range, which is very nice because you can run, if you got the beam time, several elements in one beam time. You can first analyze, for example, phosphorus, and then switch to aluminum, and then switch to iron or to calcium, and so on, which is very nice. Yeah, starting with sulfur. It was at the beginning at the ESF. I investigated a forested watershed in Germany. Very nice area with spruce forest and hilly terrain. And there's a landscape pattern which shifts between spruce forest and at areas where the groundwater is very close to the surface, we have wetlands and fens. And I selected a so-called catena of soils, a sequence of soils on a hill slope where the groundwater table got increasingly closer to the soil surface, and the soils got increasingly affected by high groundwater, which means reduced soil conditions. And the Fichtelgebirge mountains experienced a lot of atmospheric sulfur deposition in the 1970s, 1980s, up to the 1990s, and the forest died at large places due to sulfur pollution. And now there was the question, how did the sulfur behave in the soil in the long run? Was it stored? Was it stored in stable phases? Was it stored in reduced phases which might oxidize during climate change and drying of wetlands and so on? So it was a very important issue. And I selected samples from this soil sequence and looked for sulfur speciation. Sulfur is comparably nice to assess with XANES because there is a strong difference in the spectra between 2.4 and 2.5 keV. And you see that the white line is systematically shifting with increasing oxidation state from sulfides with -2 sulfur up to sulfate with +6 sulfur. And you see at the right side here, there's a linear relationship between the white line energy and the electronic oxidation state. And the spectra are comparably easy to distinguish. And so XANES is very nice to do with that element. Particularly, there's a lot of sulfur in our soils. How can you deconvolute spectra? Normally, there are two, I put away PCA now. There are two methods I was working with. One is the classical spectrum deconvolution using the Gauss method, that you simulate the spectrum of your sample by a sequence of Gaussian peak fittings plus arctangents to get the edge step. And the alternative, what you can do, is to do ordinary LCF, linear combination fitting. You analyze appropriate standards, and then you try to simulate your sample spectrum by different combinations of the different standards. And when the difference between the simulation and the spectrum is minimum, then you say, okay, that's my standard combination, which probably is present in the sample. Yeah, what to do, which is better, that depends on the element, it depends on the samples you're studying. And for soils, we did a study a couple of 10 years ago, which we published in ESNT, where we compared both techniques for analysis of standard mixtures and samples concerning sulfur XANES. The problem is that you see here with linear combination fitting, there is some samples which are present in soils, or some standards which are some compounds which are present in soils, which are simulated by a single Gauss peak, but you have to have several Gauss peaks, and depending on the organic core of your, in this case, organic sulfate, there can be different patterns which are unknown, so you don't even know how many Gaussian fittings you have to do and which ones at which energies. The problem with soils is that soil sulfur is mostly bound is soil organic matter, SOM, and soil organic matter is almost as individual as human beings. There is no two identical molecules of SOM, and this is very hard to simulate with LCF with standards where you only have a very limited selection. So for soils, even if in our study here on mixtures of different minerals, both methods performed well. If I work with natural soils, I would recommend to do the Gaussian fitting rather than the linear combination fitting, because it's the less worse option. You cannot be completely wrong, even if you don't perfectly simulate your different compounds present in your sample with Gaussian. Yeah, doing so, I must show you another important issue for sulfur and also for iron. You have to be very careful with sample preparation, because sulfur can be redox sensitive. And if you treat your soil samples ordinarily, like you go out into the field with a shovel, get your stuff, put it in a plastic bag, then put it in your drying cabinet, it will be oxidizing during the sample preparation. And the spectra you get is completely different from a spectrum which you will get if you keep your sample anoxic during the entire sampling and sample preparation step and analysis itself. So you see here nicely reduced sulfur at 2.47 keV is much more in the anoxically treated soil compared to the same sample when treated without caring for absence of oxygen. So a lot of the reduced sulfur will be artificially oxidized to oxidized forms, and what you get from your XANES results is not the truth which was actually present in the soil. So you have to be careful with anoxic sampling and maintain very difficult but rewarding steps during sampling and sample preparation. And by doing so, we got a nice feature of the effects of increasing groundwater influence in our soils. This was the most oxidated soils in the upland. This was the soil in the peat, and this was the intermediate soil. And you see, if you go down to from the upland to the fen, you see that the reduced sulfur features at low energies are increasing in percentage compared to the oxidized sulfur features. And also, if you dig deeper in the soil and approaching the groundwater, you also get an increase of reduced portions compared to oxidized portions. On converting this by spectrum deconvolution into real data, you see first, when you go down from the upland to the fen, you get an increase in sulfur concentration, because the sulfur is particularly stored as iron sulfide in fens. And when you get conditions which allow the accumulation of iron sulfide, you get much more sulfur in the same environment compared to the normal oxic situation. And you also see that the black colors representing the reduced sulfur species increase in percentage when you go from the upland soil to the peatland soil. Then we analyzed the same samples for iron, which is a little bit more complicated, because with XANES you don't get so much information compared to sulfur. As for sulfur, also for iron, the reduced iron has its edge step and also its white line as at a little bit lower energy compared to the oxidized iron. You see it in the spectra here. So iron is done at 7.1 up to 7.3 or so keV. And you see here's a set of reduced iron compounds, sulfides, and a silicate iron compound which has reduced ferrous and oxidized ferric iron. You see the sulfides, the sulfides have their signal here at this lower energy, and the oxidized, partly oxidized biotite has also some features at a higher energy. And if you compare the spectra of the reduced soil iron minerals with those of the oxidized iron soil minerals, these are mostly oxyhydroxides, hematite, goethite, ferrihydrite, lepidococite. I have here the German names, but I can understand them because it's very similar in English. And you see that the feature is mostly at higher energies, which is very similar to that at what we had for sulfur. More high oxidation state means less electrons, means you need higher beam energy to remove another electron from the core shell. And you see also, which is not so nice, that the different iron oxides have very similar spectra. So if you want to differentiate them, you cannot do it with XANES, you have to use EXAFS techniques. And we have also organic compounds in ferrous reduced and ferric oxidized states. And these are the functional groups which are most prominent in soil, citrates, oxalate of soil organic matter functional groups. And you see two things. First, the reduced organic ion compounds are different in spectral features compared to the oxidized. And it's not only the white line position, it's also the post-edge shapes. And you also see that the reduced organic ion compounds differ from the reduced inorganic ion compounds, and the same is the case for the organic oxidized compounds and the inorganic oxidized compounds. So you can nicely differentiate ion 3 inorganic from ion 2 inorganic and ion 3 organic from ion 2 organic. And doing that on our samples, we have the same pattern from the upland soil to the peat. The dark shaded reduced ion compounds increase in percentage of total contribution. So there's more iron reduced in the peatland compared, and very, very little iron reduced in the upland soil, mostly covered by iron oxyhydroxides. So the iron in our sample set, in our catena, as the soil scientists say, mirrors the pattern of sulfur, and this is logical because iron and sulfur are closely coupled in their biogeochemical reactions. Yeah, I don't have, yeah, it's almost 20 minutes, and I think we have time for a short break if you want. And I don't know, I'm not the chair, I'm just the speaker, so the chair has to decide how many questions she will permit, or if there are any questions at all. Let's see.
We have questions. Seems not. No. Maybe you can continue, George.
Okay, so let's continue with part 2. And now we are switching from the more simple elements to a more complicated one. And this is phosphorus, which causes several problems because, first, it's only present in one single oxidation state, mostly at least. It is +5, so it's only phosphate, which means you cannot make use of this energy relation between peak energy and oxidation state. All the white lines of phosphorus are at almost the same peak energy at about 2.155 keV, which is not nice. Secondly, the features of different phosphorus compounds are much less prominent compared to the features in sulfur and iron stain spectra. For example, you see, if you want to differentiate aluminum phosphates from iron phosphates, you have to look at this small pre-etch feature here. This is the difference between aluminum and iron, and maybe a little bit you see a difference in the post-etch features, but the problem is that there are organic compounds, phytic acid, which don't have post-etch features as well. So if you want to discriminate between organic compounds, phosphorus compounds, and iron 3 bound phosphorus, you have to rely on this pre-etch feature, which is particularly if you have low P concentrations, almost not visible and prone to misinterpretations. A little bit easier it is if you have calcium bound phosphate. You see you have a strong shoulder at the high energy side of the white line for all calcium phosphate compositions and compounds in soils. So you can get a comparably nice differentiation between calcium and non-calcium bound phosphorus in soils, and some idea of iron phosphate versus other phosphates. What is most difficult is the discrimination between aluminum phosphates and organic phosphorus. And what is a pity with K-edge stains, which is the most easy way to do stains, at least in my opinion, you cannot distinguish between different organic P forms. So phytic acid is just the same as lecithin or other. It's only very subtle features which I don't want to really do LCF on. And organic P dominates strongly in soil. So the vast majority of the P in soils is hidden by very featureless spectra. What you can do is you can apply LH stains. I will give you some information on this later. But the problem with LH stains is that you cannot do anything with it first with concentrations less than 2 milligrams per grams. And here, at least at Vantana's instrument, which is very good, we can go down to, if you have a lot of beam time and can run samples for a long time, down to less than 100 microgram per gram phosphorus if you have really, if you can take out time. So this is much more sensitive than L exchange. And what also is a problem for LH and to a lesser extent K exchange is that the spectrum to convolution evaluation is much more difficult because of the poor spectral features, which are more affected by noise effects in the spectra compared to sulfur and iron and other elements. And finally, there's normalization issues. So these are all normalized spectra at DC, normalized to an H step of 1. The original spectra, particularly if you have low concentrations, often look much more terrible. And it's an art itself to convert this original spectrum into normalized spectra. And you can do on the same spectrum very many ways how to do, and you end up with different results. With it, a PhD student of mine did a job on comparing known mixtures of different phosphate compounds, iron, aluminum, organic, calcium, and we tried to develop an automated process run by R to get the most exact and reliable speciation results on that. And now we can solve the problem of let's say, in a certain sense, subjective normalization. So this is an objective procedure where you can't interfere with your personal feelings. And it ends up in our mixtures with a nice representation of the true speciation. So the LCF results represent the true mixture percentages. And also, there's another problem that, unfortunately, due to the small features of your different sulfur species, you can even express one standard with mixtures of other standards, which makes the system really complicated. But a colleague of mine, Jon Tveter Gustafsson, has developed also a routine to avoid the problem and really to get the right results from your standard selection. This is, you pay the price that you have to get a rather rough speciation scheme. So you cannot say I have 9 different species in my sample, but you can maybe say this is calcium bound, this is aluminum bound, this is iron bound, and not much more than that. And a PhD student of mine, Luis Carlos Colochuratate, just recently was very successful with developing a protocol which allows to interpret the much more complicated LH spectra and get nice results for defined mixtures of different organic phosphorus compounds. The problem is, it's written down here, you have to have a content of more than 3 milligrams per gram, which is very seldom the case in forest soils, but you can work in agricultural soils which have been fertilized with phosphorus nicely with this new approach of Luis. Okay, so there's progress in soil phosphorus speciation by Zane's spectroscopy. And now I'll give you 2 examples, what I did recently. First is an example which is related to a very unpleasant but increasingly regarded feature of our world, which is climate warming. And it has very many adverse effects. And in the colder regions of our Earth, one adverse effect is that the glaciers are disappearing, which is an aesthetic thing, which is a problem for the habitats and the organisms which are living here. But it's also an issue of water supply. And I think there are already increasing troubles between India and China, what to do with the decreasing amount of glacial water in the Himalayan. And this will be ever stronger, these problems with water supply. And in Germany, there was an old We don't have too high mountains. This is a little bit less than 3,000 meters, but we had a glacier on our highest German mountain, which was quite nice 80 years ago, but it has disappeared to almost nothing. And we are now 10 years later, and this thing has almost gone. And there are serious predictions that in 2030, there won't be any glacier anymore in Germany. This is a bad thing. It has one good thing: you can conduct very nice soil and ecosystem development studies. If you approach your glacier from the downside and you sample soils when approaching the current glacier terminus, because deglaciation goes from down to up, and your way to the current glacier terminus represents a time sequence. And I did this in China at the Hailugu Glacier in southwest China. It's here. This mountain is Gonga Mountain. It's 7,500 meters high. It's the first time in my life that I have been that high, and the last time as well. And it feeds a very large glacier, Hailugu Glacier. And that glacier also has retired, here's the scale, more than 2 kilometers within the last 120 years, which is very much. And during the last 120 years, at the oldest places where the glacier had been 120 years ago, now there's already a forest. And the closer you come to the current glacier terminus, the ecosystem gets younger and younger, and the forest turns into shrubland and turns into barren moraine. I will give you, here are the pictures. Here it's the current glacier terminus. This was 10 years ago. Maybe it's now 50 meters further up. Just ice and rocks melting out of the ice. This is a little bit away. Here was the glacier 12 years ago, 30 years ago, with beginning soil formation. You see there's accumulating soil organic carbon, which means humus. The weathering proceeds, and the topsoil gets acidified, and the soil gets more and more humic, and there develops grass, and the last periods also forest. You see here the sequence of vegetation from moraine, shrubs, bushes, broadleaf forest, conifer forest. The soil gets more and more acidic. The humus contains sulfur, so the sulfur concentration increases, but the phosphorus, which is stored in the rocks and which is liberated by weathering, is consumed by the vegetation and the trees. So the soils get more and more, the topsoil gets more and more depleted by phosphorus, because phosphorus is an element of life, and the life, it extracts the phosphorus from the soil. And what we wanted to do is looking at the phosphorus amounts and the phosphorus speciation in this chronosequence. We sampled the upper mineral horizon, so-called A horizon, and the lower horizon, which is actually still rock after 120 years ago. And you see, we start with that one. In the subsoil, the young soil is characterized by a typical calcium phosphate apatite feature, and this feature is present at all places, also those who have been deglaciated already 120 years ago. So there's still apatite present and dominating the phosphorus in the soil, in the subsoil. In the topsoil, something's going on. The apatite signal disappears increasingly the older the soil is getting, and which means the apatite is dissolved by mineral weathering and plant acquisition. They excrete acids to acquire the apatite and dissolve the phosphorus and take it into their biomass. And the phosphorus gets converted into organic P, because that's what humus P is about. Very featureless, as I mentioned before, spectra without any clear signal. And to convert this spectral information into a species, you see in the C horizon, there's no speciation change. Most of the soil P is apatite P, as evident from the spectra, but there's also a certain amount of P which is obviously aluminum bound. This is logical because some P is also present in silicate lassites. And you see the phosphorus concentration goes down though. So there is some with time of soil formation. So there is some P depletion, but there is no exchange of original mineral P by humus P or so. And this is different in the topsoil. We have a strong depletion of the total P concentrations with increasing soil age and vegetation development. And also what's particularly decreasing is the apatite P. At the end, in the old soils, we don't have any apatite P anymore. And this apatite P is partially replaced mostly by organic P, but also by iron-bound P, which accumulate in the iron hydroxides and oxyhydroxides which are forming in the soil and making the soil brown. When the soil is brown, you know that it's iron oxides. And iron oxides are strong phosphorus sorbents. So a part of the phosphorus which is taken up by vegetation is mineralized by microorganisms and then attaches to the new iron oxides which have formed during soil development. That's the story. Yeah, there's a quite interesting thing what's going on in this glacier forefield. Now going back to Germany, we have a problem of increasing forest P deficiency. So our forests are increasingly getting poor in P, and this causes a problem for forest vitality and also for forest growth. And therefore, it's interesting for our foresters to know how much P do we have in different soils, and how is the P present? Can it be acquired by forest trees or not? And this was the reason why we took a large inventory from very different soils in Germany. Here you see for the non-soil scientists, soils can be very different and very aesthetic. Each soil is a particular, let's say, work of art. Yeah, you can hang them on the wall as pictures if you want. And these different patterns are shaped by different physical-chemical reactions: acidification, humus accumulation, reducing conditions, and so on. So we took different forest soils from different parent materials: calcareous bedrock, silicate bedrock, and less, which is a mixture actually of finely grained calcareous and silicate bedrock. And then we investigated the phosphorus speciation, and soil scientists are always working on horizons, which means it are these differently colored or otherwise differently shaped horizontal, that's the name, horizons, features of soil. So soils are, in the beginning, they are very unique, but as they develop in horizontally differentiated so-called sheets, yeah, and there's different phosphorus species going on, occurring in different horizons, and that's what we studied. And we turned out that the silicate and silicate carbonate soils had very different phosphorus species compared to the soils on calcareous material, limestone or dolostone. You see it by the colors. What you also see is that the phosphorus content in the most soils gets lower when you go from the soil surface down to the bedrock. This is the case because most of the soil is organic, and accumulation of soil organic matter and humus in the topsoil results in phosphorus accumulation. That's a different story than the story I told you at the glacier forefield, yeah, where I talked of phosphodepletion. Here we have a phosphorus accumulation in the topsoil. The phosphorus here in our mature soils is taken up by the plants in the subsoil and pumped up and enriched in the topsoil. And what you also see is in the silicate acid soils, most of the phosphorus is iron-bound in the topsoil and aluminum-bound in the subsoil. There's only very little, only in some soils we have some calcium-bound phosphorus. Because these soils are acid, they have been developed for several thousand years, and all the calcium phosphate, which was originally present here, has been converted into other phosphorus forms. In the calcium, in the calcareous soils, there's a different biogeochemical pattern. Also here, the apatite P, the calcium phosphate P, is mostly dissolved, but it's not converted into phosphorus by adsorbed to iron oxides, aluminum oxides, or clay minerals, but it's stored as organic calcium-bound phosphate. So it is an organic fraction, and this is hardly accessible to microorganisms. So even though there is a lot of organic phosphorus here in these soils, it's very hard for the trees and for the microbes to get that phosphorus, because these calcium phytates are very stable precipitates and which are hard to extract. And this is the reason why our limestone and dolostone soils are very poor supporters of forests with respect to phosphorus. So you see, it's a very nice pattern. Geology determines phosphorus speciation in German forest soils. And this is also the case in other forest soils of temperate regions like America or Russia also. Yeah. Here you see the phosphorus pools, mostly governed by iron and aluminum bound P in the silicate bedrock forests, and mostly calcium organic P in the calcareous bedrock forests. Now I'm almost done with my talk. The time is almost over. I will give you a glimpse of my most recent study. No, there's another thing I want to show you before. I mentioned at the beginning of my talk that the small amounts of samples needed for XANES analysis allows you to assess your P speciation not only on a horizon mode, like we did here, different horizons, but to separate, to identify spatial heterogeneity among different horizons, and also look if the horizons are really horizontal or if there is maybe other patterns in the soils. And we did this grid approach. We sampled P, we took sample in very small amounts, maybe 1 gram or so at every knot of this netting here, and could analyze all samples for XANES. This is a P-rich soil, so we didn't need too much beam time for a sample here. That's more than 1 milligram phosphorus per gram soil. And we could get a nice image of the spatial distribution of different P compounds. So total P is enriched in the subsoil. And if you approach in the soil, the surface, the soil, no, excuse me, as in other soils, we have more soil in the topsoil. So I interpreted this wrongly. So here's the topsoil P enrichment, which I talked about. But if you look at different P species, you see that's not the case for all P species. Hydroxyapatite, which is the initial lithothanic P form, is still enriched in the subsoil, but it's lost in the topsoil. And organically bound ferrihydride bound or iron bound organic P is enriched in the topsoil, and iron bound inorganic P is enriched in a little bit greater depth of the soil. This is reasonable because most of the soil organic matter is up here in the topsoil. You see it from the color, and so more of the P is also organic compared to the situation here where more of the P is inorganic. And this is nicely reflected in the phosphorus, which is absorbed to iron oxides. And you see that there are obviously hotspots, patches with increased, island of increased P concentrations in your soil, and depletion zones. And this is important for the plants because the plant roots can selectively approach these islands and mine them for P. So at the same average P concentration in a soil, greater heterogeneity results in better plant supply because the plants can really go to these places where there is a phosphorus enrichment. I could prove this with an experiment where I simulated hotspots in the soil and the plants grew better. Yeah, now I'm coming to the last part. Just started recently. It's calcium speciation in soils. In principle, calcium shows very nice features depending on its speciation. You see here at the left side the carbonates. They are carbonate minerals. They have different features compared to sulfate or fluoride minerals. And you can even differentiate dolomite, calcium magnesium carbonate, from calcite. And you can even discriminate between two calcite forms, between two calcium carbonate forms, calcite and aragonite, which are formed under different environments. So this is very nice. And you can also differentiate different other calcium minerals which are present in soils. Calcium phosphate, we know it from the phosphorus side, the apatite. These are other calcium phosphates, which all have also, again, this post-edge feature. As for phosphorus, there's also some feature for calcium. We have silicates, augite, epidote, and anorthite, and clay mineral. They have slightly different features compared to these phosphates, and very, very different features compared to the evaporites mentioned here. So you can discriminate different soil minerals nicely by the spectra. And if you look at the right side, we have different organic calcium compounds in soils. So plants enrich calcium in their tissue, and it's mostly bound to the carboxylic groups of their plant tissue. And depending on the type of carboxylic group, there is slight differences in the spectra. They are not really strong, but what's nice is that calcium oxalate has a different feature compared to the other calcium carboxylates. I will show it in the next slide. So these are different calcium organic species which can be found in soils and in plant tissue as well. And calcium oxalate has two prominent features which are different from the others. First, it has this higher signal intensity at 4090 eV, and compared to the other carboxylate, it has a less pronounced shoulder at this time. So a combination of both allows differentiation between calcium oxalate and non-calcium oxalate organic forms in soils. The other compounds are more difficult and unreliably to discriminate, and I wouldn't bet on a sound quantification for that because the spectra are somewhat different, but not really different. And then I used this information to study the calcium speciation in a soil formed from limestone. It is a soil formed from calcite. You see here the typical feature of the calcite bedrock. And then I took samples in the different horizons. Here's the topsoil, here's the soil surface. This is the litter layer, fresh litter from plants growing there. OF is the humic surface layer on the soil, slightly decomposed litter, like if you put stuff on your compost and watch it after half a year. And then it's the mineral topsoil, and then you're going into the mineral subsoil. And age here means that there's still some soil organic matter in the mineral soil that mixed by earthworms and other animals. And you see from the bedrock up to the L layer, the spectra change. The calcium carbonate signal disappears and is absent in the upper three horizons. And if you and other features are appearing instead. And if you convert the spectrum by LCF into species information, you have the legend here. You see that the carbonate calcium decreases from 100% in the bedrock, which is logical, to almost nothing in the topsoil, which is also logical. And then you have an accumulation of iron-bound, clay mineral-bound calcium in the upper soil. Soil formation on limestone means that the limestone is actually dissolved, and there are very small amounts of accessory minerals in the limestone. And these are enriched by the dissolution of the matrix. So you get a so-called carbonate dissolution residuum consisting of clay minerals, iron oxides, and quartz in the topsoil. And the calcium remaining in the soil is here bound to these clay minerals. And you see the percentage of organically bound calcium to total calcium increases strongly when you approach the topsoil. And I wouldn't bet too much on this discrimination here. I've just printed it and it was accepted by the reviewers, but I wouldn't bet too much if it's really 90%, 10% pectate or 15 or so. But you see, there's calcium oxalate and non-oxalate in the topsoil. And when the soil develops, the calcium dissolution front moves more downward, and the accumulation of clay minerals also moves more downward, which means that the entire feature moves downward. So only here it is in this cambisol from cambiare, or cambio, it's a word for change, Latin word for change. The soil has changed from a calcareous soil to a ripe, mature soil. The bedrock has disappeared in all horizons except the most lower ones. Here we have clay-rich, brown, iron oxide-rich, fine material horizon, and the calcium here is mostly bound to clay minerals. And of course, in the upper topsoil, most of the calcium is organic. Yeah, so calcium XANES allows nicely to monitor the changes of calcium species with soil formation, and also to discriminate different soils. At the end, I will finish my talk with this problem where I'm currently working on and where I haven't still at the moment not found a real solution. But before that, I will just summarize again what I got from that study. In the beginning, initial soils, the calcium is mostly present as carbonate. With soil formation, the carbonate disappears, the residuum accumulates in the soil, A and B horizons are formed, and the calcium gets more and more not bound to carbonate anymore, particularly in the upper horizons, but to clay minerals and to organic compounds. And if you wait for a longer time, also this carbonate calcium will disappear and will change into clay mineral calcium. Yeah. You can also work, the theme of my talk was also in other environmental samples, and I will give you a short example on tree foliage and tree roots. I analyzed tree foliage of different tree species. This is broadleaf, maple and beech, and this is conifer, spruce and fir. And I analyzed the needles and the leaves. And what you see here again, the different pattern of the spectra of the conifers, more pronounced hump here compared to the broadleaves. And if you convert this information into calcium speciation information by LCF, you see that the conifers have much more oxalate compared to non-oxalate in their leaves compared to the broadleaf. So there are and these are different trees sampled from different areas. So it's not an area issue, but it's a tree species issue. Conifers have more calcium as oxalates in their leaves compared to broadleaves. Because the reason is oxalate is a passively accumulated element in foliage. So the trees take up calcium with their roots. They don't want so much calcium, but they have to take it up and they have to dispose it somewhere. And they have two different strategies of disposal. Broadleaves, they shed their leaves once a year and develop new leaves, and new calcium can be disposed and cycled. And spruce needles, spruce tree or conifers, they have their needles for several years, up to 8 or 10 years before they shed their needles. So there's more oxalate accumulating in these needles just by transpiration effects, which means that the percentage of the contribution of oxalate calcium to total calcium is higher in the conifers compared to the broadleaf trees. And also the fine roots of the different tree species are slightly different for broadleaf and conifers, but in a different way. Obviously, we have citrate present in the conifer, but not in the 3 beech trees. If this is just coincident or not, I don't know at the moment, but at least there was some different patterns. Yeah, now I'm coming to the problem which I'm currently working on. This is the problem that calcium is a divalent ion, a divalent cation. It is calcium 2+ in soils. Not elemental calcium, then it would be problematic. It's calcium 2+. And divalent ions, cations, can use their 2 charges by binding either with both charges to the same counter element, or they can, like a human being, take one hand to person 1 and give the other hand to another person. And then you run into problems with spectrum deconvolution. For example, we have a simple case where we have calcium only bound to one partner. It is like if I give my both hands to my wife. Yeah, no problem. LCF, and this is another person, colleague of mine, who gives his hands to the calcium, to the carbonate partner. And LCF clearly can distinguish if I have 2 calcium ions here with citrate and 4 calcium ions here with carbonate. LCF will nicely report this. The problem now is, as in human relations as well, if there's mixtures, if one person sticks to 2 persons instead of only one, then the person will end up in problem. And in chemistry and in XANES technology, the person who has to deconvolute the spectrum ends up in problem. What are you doing with a situation like that? So we have again 6 calcium ions. One is associated to citrate, 4 are associated to carbonate, and 1 is associated to both. What do you do now? Do you say, okay, I have, if you count, 1, 2, 3, 4, 5 to carbonate, 1, 2 to citrate. So 5 of the 6 are carbonate associated, and 2 of the 6 are citrate associated. Then you normalize it to 100%, you end up with this result. If you say, okay, I simulate that half of the charge is associated to this one and half of the charge is associated to this one, to that one, I say, okay, 4.5 calciums are carbonate and 1.5 are citrate. You end up with this result. And if you say, okay, this is entirely carbonate bound, this is entirely citrate bound, and this is half calcite and half citrate bound, and you try to develop a standard for this, for a combination, for a calcium which is bound by two different partners, and inject your standard in your LCF fitting, and you work correctly, then you would end up in this result. So it's, at the moment, I don't really know what is the ideal way to deal with these mixed relationship issues, which are very, very prominent to occur in soils, I guess. And which also mean that the results which I showed you here are probably not completely correct, because I have not addressed this issue in these calculations. Yeah, so I'll leave you with this foot for brain, and maybe one of you colleagues will give a talk soon solving this question for me. I'm done with my talk now, and I will summarize the main results, which are positive. Again, you always should leave the audience with a positive instead of a negative information. Synchrotron-based XANES spectroscopy is a powerful tool for direct non-invasive speciation of important bioelements in soil and other environmental samples. I think I could show this to you with my case studies. It opens new perspectives for soil science, but also for other earth and life sciences like geology, biology, agronomy. And finally, I hope for all of us that the new knowledge gained by XANES spectroscopy may hopefully contribute to more improved sustainable utilization and management of natural resources and Earth itself. So as far as I see it at the moment, we don't have only a minor problem of recognition of problems, but we have a major problem of converting our knowledge on the problems, on solving them. Yeah. I thank you for your attention, and thanks again for inviting me to this XF Club talk. I'm happy to take questions.
Thank you, George. Chris, your microphone, please. Okay.
Yes, I think I've got it. Jörg, you can hear me?
Yeah.
Fantastic. Excellent talk, very interesting and quite informative. So thank you. Now, there were two things. One, you were talking about the challenges of getting the right thickness of soil sample for your experiment, your beamline and so on. And of course, that depends on the beamline and various other things too. But of course, if you can characterize and correct for self-absorption, which might be a topic in one of the future talks, so that could be relevant, then that can help give you both more accuracy and insight, but also then tease out a couple of these details. So that can be quite helpful. That's my first comment. The second one is relating to your puzzle at the end. And I think I might just comment that, yeah, having many reference samples or too many references doesn't necessarily help, yeah. especially if you're in the XANES region. However, if you can collect by whatever conditions and so on, reference and or good XFs across a fuller range to a higher K, then not only can that isolate, is this a pure system with a particular coordination and environment, or the other one, but it can also separate some of the mixtures by being able to see the different shells, mixed shells at different radii. And so that's a partial answer, because then it wouldn't be XANES exactly, it would be XFs. And whichever package that you might be using, of course, have advantages and disadvantages, but that is one way of solving that problem. Although, of course, it's more labor intensive and it's more beamline intensive. That's what I wanted to suggest.
Yeah, thank you very much for your two comments, which are both very valuable and important. Concerning self-absorption issues, there's, as probably most of you know, two issues. First is the thickness issue, and the other one is the concentration issue. That it makes a difference if your element is finely dispersed, evenly dispersed, or if it's enriched in certain hotspots in your samples. It's may cause self-absorption even if the total concentration is low. The problem, as far as I know, is with self-absorption correction protocols. They work nicely in situations where you know what material you're working with. You can, if you have the chemical and the quantum mechanical background, you can calculate what self-absorption occurs in your sample. In soils, which are a very heterogeneous mixture of unknown compounds, it's very hard, at least to my knowledge, to use these calculation routines for an appropriate correction of self-absorption. So I think I read it in the famous environmental XANES book. I think it was Dean Hesterberg. It's better to avoid self-absorption than trying to calculate the confounding effects of it, in soils at least. Concerning your next, yeah?
I think you're right. If it's too heterogeneous and too variable in a local environment, it makes it very difficult to understand and interpret. A part of it can be done, if you like, empirically, as in to reverse it. But if it gets too complicated and too mixed, then you'll be in trouble. I agree.
Yeah, what we try to do normally is we combine our measurements with a sequence of increasingly concentrated standards. And then we look at which point of concentration we have a serious change of the spectral patterns. And we try to dilute our samples with boron nitride or with quartz to be well below this critical concentration threshold, at least to assume that self-absorption isn't too big an issue in this case. Of course, we can never completely avoid it. I mentioned this because to this micro concentration effects and so on. But maybe it's really worthwhile to invest more brain for me as a soil scientist. So these calculation issues, so FEFIT and other things, they are more easily doable for physicists who are trained on that than for soil scientists. But maybe we should invest more time and brain dealing with these programs and apply them. You're completely right. I'm just somewhat deterred of that. Yeah, so I'm coming from a different profession. That's so integral equations, I don't like too much. Yeah, and the other issue, it was your puzzle and the solution to apply XFs, which in principle would really be very, very nice to do. The problems, at least for ordinary soils, if you don't work with artificial soils, which have only particular compounds and avoiding others, is that your XF signals would be confounded by other features of higher elements. For example, if you do sulfur, if you do phosphorus stains and want to skip to XFs, your signal would be confounded by the following sulfur signal. And most soil samples have much more sulfur in their soil matrix than phosphorus. So this limits to some extent the use of XFs. But at least maybe we should to look how the system is really functioning. We could work with well-defined systems. For example, for the calcium divalent bonding issue, we could work with so-called soils, artificial soils, which only contain carbonate, citrate, and calcium. And then XFs really, I completely agree with you, would be a nice tool to address this question. And then say, okay, very, very likely the soils are behaving in a very similar way as our artificial mixture has done. Yeah, that would be maybe that's the way to go. Thank you.
I think there was a question maybe or comment from Kiyotaka as well.
Okay.
Yes.
Thank you very much, Joe. My question is about the calcium KH ZANES, and you show the pre-age peak for all calcium KH. That is related to some symmetry or structure.
I think so.
Mm-hmm.
Normally, the pre-age peak always represents some symmetry or
Yes.
transition issues. But as I mentioned before, I'm not a physicist, and I have at the moment approached the calcium ZANES issue from a practical view by just I'm just at the beginning stage using it for spectrum for speciation. And the next stage, which may be better be conducted by people who are more trained in that, will be really explaining the underlying phenomena and physicochemical patterns which create the different pre-etch and also the post-etch features in the different calcium compounds.
Yeah. So yes, I am doing the iron KH case, the tetrahedral iron, give the large peak. But in your calcium, I know the octahedral structure is basically octahedral structure, and there's some peak, so it means some distortion or something.
In the case of the carbonate minerals, it's probably the case, but in the soils, most of the calcium, at least when the soils are developed to a more mature stage, there are no well crystallized calcium compounds anymore. Most of the calcium is bound to organics in an irregular shape and maybe adsorbed to clay minerals. But for the carbonate fractions, there's surely clear crystal lattices with different and clearly identifiable effects on the pre-etch phenomena, like you reported is for iron 2 and iron 3 compounds, where you even can, with iron, I know you can even rely completely on the pre-etch phenomena by if you want to deconvolute your spectrum. You don't have to look at the white line and the post-etch. Maybe this is possible for different carbonates as well, in pure mixtures, but I haven't occupied myself with that at the moment. But it's a good idea for mineralogists and geologists maybe to do so. Thank you.
Okay, thank you very much.
More questions?
We have questions from Dr. Mariko Petrik in the chat.
Okay. Go ahead.
Yeah, can a similar analysis being done with X-ray emission spectroscopy? I'm not an expert in this. I would assume so, but maybe some other people of the audience can give a more precise answer. Maybe one of the physicists.
Thank you.
Can I ask a question?
Yes, please.
Yeah. Okay. Very nice talk. I learned a lot from the speaker and also the discussion with the Professor Chandler. So I'm also wondering, in your one PPT slide, you talk about the phosphite, the LH. So I'm wondering what kind of information can be received from this kind of beating, especially for your soils.
Yeah. As I mentioned before, in most soils, the majority of phosphorus is organically bound. And up to now, the only way to speciate the organically bound P is PNMR, and this PNMR spectroscopy, and this cannot be done on the soil itself, but you have to extract the soil first. And then you come into the problems which I mentioned at the very beginning. You don't extract the entire stuff. Do you extract a representative portion or not? What is the residual like? And it's very complicated. So it would be really desirable to directly assess the organic P without extracting the soil before.
Okay, I see.
This is the would be the main advantage of the non-invasive XANES techniques.
I see.
Did I answer your question correct?
Yeah,
fully,
sure,
or-
sure.
Okay.
Yeah, sure. I understand. So the second question is about you discussing with the Professor Chandler about the combine the science with the XANES. So you're talking about they have the really complicated structure in your materials. So this means you do not have the model materials, maybe model soils for your study. So is there any possible to, for example, to start from simple to complicated to make this is a rule, especially, combine the sense with the XANES should be give you the coordination number, coordination bonding, and all local structure, and together with the oxygen state, right? I'm just wondering.
Yeah, thank you for this very inspiring question. I think one good approach to a nice answer would be it depends. It depends. First, which particular soil are you studying? And second, what do you want to study? So there are situations where you are probably completely helpless with XANES. If you want to study, let's say, iron minerals associated to soil organic matter in humic topsoils, where the iron minerals are not present in a regular shape, crystal shape, but are so-called X-ray amorphous, and the organic matter completely messes up any present regularity of structure. It might be completely different if you want to study the adsorption of sulfate, of phosphorus,
I see.
or also of chromium to iron oxides, to goethite or to hematite, which are well shaped and which may be really enriched in particular horizons to an extent, or already reminding to iron ores, where confounding effects of other elements are not really playing a large role anymore. Their XANES might be really a good tool to reveal patterns which are hidden by XANES.
Yeah, exactly. Okay, thank you very much. Thank you.
You're welcome.
I think we have some question in the chat box.
Yeah.
The chat box.
Okay, yeah. I have two questions regarding Gaussian curve fitting of sulfur case spectrum. How can we know that the deconvolution result is good enough? By looking at the fit line or the residual line. Starting with that one, I think that the residual line gives you a much clearer view of divergences of the spectrum from the sum of your Gaussian curves at any given energy. I think my eye at least, does a better job in detecting differences from the zero axis than detecting small differences between two spectral lines. So I would go to the residuum, but the other part of question one, good enough? There's never a good enough. There you have to be satisfied with some state you can reach, and then you have to decide, can you with good conscience present your results to your scientific community or not, and leave it up to the reviewers to either say, okay, that was a good work, or to say, what did he do? So there is no objective way, at least in soil science, to say this is good or this is not good, because you don't know the truth, as in very simple systems where you might know this cannot be true at all. Of course, there are some boundary conditions where you know you are on the wrong way. For example, you always should compare your speciation results with elemental analysis. And if you end up with species which are, according to the elemental analysis, impossible, then you know you're on the wrong way and should probably try to a better approach, another approach. But it's very difficult in soil to say you are wrong or you are right. Coming to question 2, can the geosphere be the biggest can the geosphere be the biggest sulfur battery, biogeobattery? Oh, that's beyond my knowledge, I must say. I'm a soil scientist and not a geologist. As far as I know, soils cannot be a biobattery. That's what I can say honestly, because never ever I have read a paper even promising things like that. With geology, I don't really know. It's just beyond my scope. Maybe you should ask a geologist or a geophysicist on this question. But I'm sorry, I cannot give an answer on part 2 of your question.
Okay. It's 15 minutes, 17 minutes, sorry, for questions we have so far. Any more questions? Maybe not. Okay, so I think we should close the session. And thanks you guys once again for participating in this seminar. Very nice and very excellent talk from Professor Jörg Prietzel. Thank you once again. Thank you, George.
Thank you very much for attending me. And I'm really happy to have given this presentation. I liked it very much. And also the questions were inspiring for me, and the solutions, particularly the solution given by Professor Chandler, inspired me for my future work. Thanks.